In the serene silence of space lurks a discovery that raises a million questions. Imagine a region of space where the rules seem to have been rewritten, where a celestial anomaly hints at the existence of a cosmic giant, a black hole known as Gaia BH3. Black holes have long attracted the curiosity of scientists and everyday people alike. These mysterious objects of the universe exert such a strong gravitational pull that even light cannot escape their grip. By anchoring themselves in the fabric of space-time, they affect the environment in a subtle yet profound way. But how would such a discovery affect us, only 2,000 light-years away? Could this silent neighbor have any impact on our solar system? Or does its presence only expand the cosmic mysteries that surround us? So we all know that deep in the universe, black holes exert a gravitational pull so strong they bend the very fabric of space-time. These cosmic mysteries are not just points in space, but dynamic regions where gravity is so strong that the ordinary laws of physics have trouble holding it together. But let's understand the nature of these celestial phenomena in more detail. The gravitational force of a black hole is indeed powerful. It's what causes space-time to warp and light to be delayed. But its influence, however powerful, is constrained by the vastness of space. The idea that a black hole can simply roam the cosmos, devouring stars and galaxies, is a misconception often propagated not by science but by sensationalism and movies. The reality is that the gravitational influence of black holes does not extend indefinitely. On the contrary, their influence decreases sharply with distance. So even black holes relatively close to our solar system, such as Gaia BH3, don't pose an immediate threat. To make sense of this, we turn once again to history. More specifically, the story of Cygnus X1, the first black hole to be discovered and confirmed. The story begins with not just a discovery, but with a daring wager in the world of astrophysics. It was the late 1960s, an era of celestial exploration and fierce debate among scientists. Cygnus X1 was first detected as an unusually strong X-ray source by a sounding rocket launched in 1964. This source was not just another point of light in the night sky, but a source emitting X-rays with an intensity that outshone almost everything else in the celestial sphere. The intrigue escalated when two of the most brilliant minds of the time, Stephen Hawking and Kip Thorne, made their now famous bet. Thorne bet that Cygnus X1 was a black hole, and Hawking bet against it, hoping to be proven wrong as part of his deep quest to understand these cosmic phenomena. This wager symbolized the scientific curiosity and somewhat playful rivalry that drive many scientific discoveries. Cygnus X1 is part of an X-ray binary system consisting of a blue supergiant star and what is believed to be a stellar mass black hole. The intense gravitational pull of the black hole pulls material away from its stellar companion, which spirals into the black hole, heating up to millions of degrees and emitting X-rays. These emissions have allowed astronomers using instruments such as the Uhura satellite launched in 1970. The first satellite, by the way, specifically designed to study X-ray sources, to study the properties of this mysterious object more closely. The Uhura satellite, being the first space telescope, has provided convincing evidence that this object is indeed a black hole. Moreover, the first of its kind. Cygnus X1 has taught us much about the nature and behavior of black holes, particularly how they interact with nearby matter. It serves as a crucial point of reference in the study of Gaia BH3. Despite the large mass of Gaia BH3 had a whopping 33 solar masses, it remains a silent observer in space, primarily because of its considerable distance from a star capable of providing material for an accretion disk. This distance suggests a lack of appreciable X-ray emission and a quiet existence, in stark contrast to the dynamic environment around Cygnus X1. While Cygnus X1 is about 7,000 light-years away from Earth, Gaia BH3 is closer, at a distance of about 2,000 light-years. Despite this proximity, Gaia BH3's passive nature and our advanced understanding of black hole mechanics give us confidence in its safety. Through the lens of the history and advances in the study of black holes, we see that these amazing objects, while powerful, are constrained by the laws of physics, making the fear of them as interstellar predators unfounded. So in the relentless quest to understand our universe, the Gaia telescope has become a key player in the latest chapter of space exploration. Designed to map stars with unprecedented accuracy, it has brought a new player into the cosmic arena. The massive black hole Gaia BH3, now the closest black hole to us. A mission to map more than 1 billion stars has given us a clearer picture of our galactic neighborhood than ever before. It was during this careful survey that the telescope discovered an anomaly. A star whose motion could not be explained by ordinary celestial mechanics alone. This star, seemingly invisible, indicated the presence of something massive, hidden from view. And who is the culprit? Why, Gaia BH3, a previously unseen black hole, hiding in the galactic halo about 2,000 light-years away. Gaia BH3 is not just a black hole, it's a colossus of the cosmos, with a massive 33 solar masses. This discovery places it among the heaviest stellar mass black holes found in our galaxy. Its location in the galactic halo, a region populated by older stars and globular clusters, adds to its intrigue by suggesting a different origin or evolution from black holes found in the galactic disk. One of the most mesmerizing aspects of Gaia BH3 is its silence. Unlike infamous black holes that make their presence known by devouring nearby matter and spewing X-rays, Gaia BH3 remains eerily quiet. The key to the silence lies in its isolation. The black hole's companion star orbits at a safe distance, too far away to be torn apart and fall into the typical perdition spiral that forms an accretion disk. This distance prevents any significant material transfer, and as a result, Gaia BH3 lacks the usual signs of black hole activity, such as the powerful jets and strong X-ray emission seen in systems like Cygnus X1. The recent discovery of Gaia BH3 not only expands our catalog of known black holes, but also sheds light on the mysterious process of black hole formation from metal-poor stars. Metal-poor stars, composed mostly of hydrogen and helium with scant traces of heavier elements, represent an early generation in the stellar history of the universe. These stars, due to their minimal metal content, lack the materials necessary for heavy element synthesis processes, which significantly affect their life cycle and demise. The star orbiting Gaia BH3 has been identified as metal-poor, which is a crucial clue to understanding its evolutionary path and the nature of its colossal companion black hole. Typically, the fate of a massive star involves a supernova explosion heralding the death of the star and the birth of a neutron star or black hole. For metal-poor stars, however, the scenario can be significantly different. The reduced opacity due to the lack of heavy elements allows the stars to retain most of its mass, leading to a higher core density and direct collapse into a black hole after death, without a spectacular supernova explosion. This direct collapse pathway suggests how Gaia's companion BH3 could form a black hole that's significantly more massive than those typically formed from more metal-rich progenitors. These direct observational data support broader theoretical models of astrophysics that predict that metal-poor environments favor the formation of larger black holes. These results are of great importance because they can explain the existence of supermassive black holes that appear to have formed rapidly in the early universe, refuting previous models of black hole growth that required longer timescales and multiple mergers. By studying Gaia BH3 and its stellar companion, astronomers are gaining invaluable insights into the primordial conditions of the universe, when such stars were more common. The discovery not only links past processes of star formation and death to the phenomena observed today, but also helps close gaps in our understanding of the distribution and density of black holes in the cosmos. However, science doesn't stand still. And most recently, in an amazing fusion of artificial intelligence and astrophysics, researchers led by the California Institute of Technology have pushed the boundaries of black hole observations. This team has successfully applied advanced AI technology to visualize in 3 dimensions the flares that often burst out of such objects. Using data from the Atacama Large Millimeter Array, the team focused on Sagittarius A, the supermassive black hole at the center of our galaxy. They observed flares, bright, energetic emissions that occur several times a day around black holes. These flares, although previously detected, have never been visualized in 3 dimensions until now. To achieve this goal, a team at the California Institute of Technology has developed new computational visualization tools that incorporate artificial intelligence techniques tailored to astrophysical data. These tools have been designed to solve the unique problems associated with the intense gravitational fields of black holes. A key innovation was the adaptation of a technique known as NRF, or Neural Radiance Fields, which was originally used in computer graphics enhancement. NRF helps create 3-dimensional scenes from 2-dimensional images, and the technique is ideal for astronomical data, which is usually limited to such images. By applying NRF, the researchers were able to simulate how light is bent in the black hole's immense gravity, creating a realistic model of the flare in 3 dimensions. The Dr. Katie Bauman team used a unique dataset obtained with ALMA, following an eruption near Sagittarius A observed in X-rays on April 11, 2017. ALMA collected crucial radio wavelength data for 100 minutes. This dataset was crucial in providing the fundamental observations needed for this study. The task of the AI was to reconstruct the 3-dimensional journey of gas bursting out of a black hole, despite the limitations inherent in observing such phenomena from Earth. Typically, observing celestial bodies in 3D requires the use of multiple perspectives, which is not possible when studying distant black holes. AI has bridged this gap by modeling these angles. The team used an improvised version of the NRF adapted for use in astronomy. This modified NRF was adapted to account not only for the light curvature caused by the black hole, but also for the expected behavior of the gas surrounding it. This method, similar to having a stationary camera take multiple angles of a rotating object, allowed the AI to predict the structure of the flare over time based on how the gas would move and how its light would be lensed by the black hole. The visualization showed 2 bright objects orbiting at a distance of about 75 million kilometers from the center of the black hole, half the distance between the Earth and the Sun. These objects provide tangible insight into the dynamics around black holes and confirm theoretical predictions about their behavior under extreme gravitational forces. The integration of artificial intelligence has not only involved visualization, but also physics-based machine learning. This approach uses knowledge of black hole physics to guide AI to reconstruct three-dimensional structures from the data, taking into account the dynamic motions and transformations of the gas in the vicinity of the black hole. This technological breakthrough provides a deep understanding of the behavior and properties of matter orbiting black holes. Understanding the three-dimensional structure of these flares helps astrophysicists better understand how matter behaves under such extreme conditions, including how it moves, heats up, and eventually accretes onto the black hole. The future of black hole research is on the cusp of a new era, fueled by the latest discoveries and technological advances. Techniques developed to study black holes such as Sagittarius A and Gaia BH3 are giving astronomers powerful new tools to detect and analyze other black holes that remain hidden or dormant. Such black holes are not actively accreting material, making them incredibly difficult to detect with traditional observational methods that rely on detecting radiation from heated accreting material. Also, by mapping the environment near black holes in 3 dimensions, scientists will be able to explore fundamental questions about the nature of their gravity and dynamics. This understanding is crucial for testing the predictions of the general theory of relativity and could inform future observations and missions. In addition, each observed black hole provides valuable data about the history and structure of our galaxy. By studying the properties and behavior of black holes, especially those formed from metal-poor stars or located in unusual parts of the galaxy, such as the halo, astronomers can infer the formation and evolution of the Milky Way. This technological breakthrough sets a precedent for future astronomical observations. By merging artificial intelligence and physics, astronomers will now be able to study other celestial phenomena in unprecedented detail, paving the way for further discoveries, heralding a new era in the study and understanding of the most mysterious phenomena in the universe. Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomenon in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. Well, the Sun is currently a stable main-sequence star slowly converting hydrogen into helium. Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion-year lifetime. The discovery of the boat GRB, also referred to as the brightest of all time in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The boat GRB, officially designated GRB 221009A, was detected on October 9, 2022 and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. BOAT was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of such cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of a gamma-ray burst. The BOAT GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While BOAT GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days. And the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shock waves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter, dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Imagine a civilization so advanced that it can build colossal structures around stars, capturing their energy and using it for unimaginable purposes. This is not the realm of science fiction. It's a concept proposed by one of the most brilliant minds of the 20th century. A visionary physicist, Freeman Dyson, envisioned a megastructure capable of enveloping a star, capturing its vast amounts of energy. This idea, while radical, is rooted in the basic principles of energy consumption and technological progress. But why would an advanced civilization need such a structure? As our civilization advances, Our energy needs grow exponentially, but our most ambitious projects pale in comparison to the energy output of our Sun, which releases more energy in 1 second than humanity has consumed in its entire history. Imagine harvesting every bit of a star's energy, turning it into a power plant with nearly limitless potential. If realized, this colossal undertaking would revolutionize how we think about energy and its possibilities. But what would such a structure look like? And even more intriguingly, how would we be able to detect it from our distant vantage point here on Earth? The problem lies in our ability to detect signs of such advanced engineering. While we are just beginning to tap into our planet's energy resources, discovering such an advanced civilization is exciting and frightening. Recent research has revealed unusual infrared signals from 7, sparking debate and fueling imagination. Could these signals be techno-signatures? Either way, these anomalies defy natural explanations. What's behind these mysterious infrared glows? Are they evidence of advanced extraterrestrial engineering or natural phenomena that we've yet to understand? To understand the concept of Dyson spheres, we must first familiarize ourselves with the Kardashev scale, a method of measuring a civilization's level of technological development based on its energy consumption. In 1964, Soviet astrophysicist Nikolai Kardashev proposed this scale, dividing civilizations into 3 types, depending on their energy consumption. Type 1 civilizations use all the energy available on their home planet, including geothermal, solar, wind, and other natural energy sources. Imagine controlling the power of earthquakes and volcanoes to power our cities. This is the hallmark of a Type 1 civilization. Civilizations of the second type go even further, receiving energy directly from their star. This is where the Dyson spheres comes into play. By surrounding their star with massive structures, these civilizations can use almost all of its energy. Type 3 civilizations, in turn, are even more advanced and can harvest and harness the energy of their entire galaxy. They control the energy of billions of stars, making them unimaginably powerful. The relevance of the Kardashev scale to Dyson spheres lies in the connection between energy consumption and technological progress. As civilizations evolve, their energy needs grow exponentially, forcing them to develop ever more ambitious methods of meeting those needs. But how can we discover the Dyson sphere? One of the most significant milestones in cosmic observation, the development of infrared astronomy, can help us in this challenging endeavor. Infrared astronomy allows us to see the universe in a new light, literally. By observing the infrared spectrum, scientists can detect heat emitted by celestial objects and reveal details invisible to traditional telescopes. This capability has played a crucial role in the search for techno-signatures, signs of advanced civilizations beyond Earth. This journey began in the mid-20th century, when astronomers used infrared sensors to study space. These early works laid the groundwork for today's sophisticated infrared observatories, such as the Wide Field Infrared Survey Explorer, WISE, and the James Webb Space Telescope. These instruments have opened a new frontier in astronomy, allowing us to detect faint thermal signals from distant stars and galaxies. But what does this have to do with the search for Dyson spheres? Well, in the 60s, theoretical physicist Freeman Dyson proposed an audacious idea. An advanced civilization could build a massive structure around its star to capture its energy. He envisioned a swarm of solar collectors or habitats orbiting the star and forming what we now call a Dyson sphere. But how could it possibly be detected if it blocked the light of its star? Of course, such a structure would emit vast amounts of infrared radiation, making it visible even from Earth. Dyson's hypothesis was more than just a thought experiment. It provided a viable way to search for intelligent extraterrestrial life. By surveying the excess infrared radiation around stars, we could find evidence for the existence of these colossal structures. This concept led scientists to the recent discovery of several stars with unusual infrared emission. Modern infrared astronomy opens new horizons in the search for Dyson spheres and other technosignatures. By observing the universe in the infrared wavelength range, we can detect thermal emission from celestial objects, allowing us to understand phenomena invisible to traditional optical telescopes. One of the most important instruments in this work is the Wide Field Infrared Survey Explorer. Launched in 2009, WISE has revolutionized our understanding of the infrared universe. Its mission is to map the entire sky in infrared light, revealing countless celestial objects, including stars, galaxies, and asteroids. This is a mosaic of the images covering the entire sky, as observed by the WISE, part of its all-sky data release. WISE's ability to detect excess infrared emission around stars plays an essential role in the search for Dyson spheres. By analyzing the heat signatures recorded by WISE, scientists can identify stars with unusual infrared emission, which may indicate the presence of advanced megastructures. One prominent example is the Hephaestus project, led by a team from Uppsala University. This ambitious initiative aims to identify potential candidate Dyson spheres by analyzing Gaia, 2MASS, and WISE data. Hephaestus uses a sophisticated system to sift through millions of stars in search of those with excess infrared emission that natural phenomena cannot easily explain. The project uses machine learning algorithms, including convolutional neural networks, to weed out false positives and identify the most promising candidates. The project's methodology is rigorous. It begins by collecting data from several sources, including precise measurements of the position and distance of the stars using Gaia, near-infrared 2MASS observations, and mid-infrared WISE data. This comprehensive dataset allows the team to create detailed models of potential Dyson spheres. The team then uses a grid search method to compare the observed data with theoretical models. This involves calculating the expected infrared emission for different configurations and temperatures of Dyson spheres, and then comparing these models to the observed infrared excess. Through this careful process, Hephaestus has identified 7 potential candidates for a Dyson sphere. All of these objects are M-dwarfs, stars known for their relatively low luminosity, making the detection of infrared excess even more intriguing. These findings are significant because they demonstrate the potential for using long-standing astronomical data for such detections. The quest to detect Dyson spheres and other technosigns is driven by ongoing advances in infrared astronomy. These innovations allow us to explore the universe with unprecedented precision and detail. One of the most significant breakthroughs in infrared astronomy is the development of adaptive optics and advanced sensors. Adaptive optics systems correct for distortions caused by the Earth's atmosphere, providing clearer and more detailed images of celestial objects. This technology is vital for isolating faint infrared signals from background noise. In addition, integrating machine learning algorithms into data analysis has revolutionized our ability to sift through vast amounts of astronomical data. These algorithms can identify subtle patterns and anomalies that may indicate the presence of technosignatures. Among the most revolutionary achievements is the James Webb Space Telescope, which has already managed to change our understanding of the cosmos in more ways than one. With its advanced infrared capabilities, the JWST allows us to look deeper into space and time than ever before. JWST's primary mirror, which is more than 16 times larger than the WISE mirror, combined with susceptible infrared instruments, can detect the faintest thermal signals from distant stars and galaxies. Essential is the telescope's ability to observe in the mid-infrared region of the spectrum. If they exist, Dyson spheres are likely to emit heat in this range, making them visible to JWST. By scanning the sky for these infrared signatures, JWST could provide compelling evidence for the existence of advanced extraterrestrial civilizations. However, its busy schedule, planned months in advance and filled with many other important research projects, limits the amount of time for searching for Dyson spheres. Radio astronomy, in addition to infrared observations, plays no small role in the search for technosigns. The Very Large Array in New Mexico is one of the world's premier radio observatories, capable of detecting radio waves across the universe. Radio waves can provide important information about the presence and nature of technosignatures. For example, a Dyson sphere may emit infrared radiation and radio signals as a byproduct of energy harvesting processes. VLA can detect these signals, offering a different but complementary perspective to infrared observations. Developing and implementing advanced technologies will only improve our ability to find technosignatures. However, the results of the team from the Uppsala University are not isolated. Another recent study entitled A Data-Driven Search for Mid-Infrared Excesses Among 5 Million Main Sequence FGK Stars by Gabriela Contardo and David W. Hogg found 53 stars with significant infrared excesses. This large-scale search also used Gaia, DR3, 2MASS, and WISE data to detect anomalies in the mid-infrared range. The technique involved training machine learning models to predict expected infrared magnitudes based on other stellar characteristics. Stars in some bands appeared significantly brighter than predicted, and thus were flagged as potential candidates. After applying additional filters to help avoid false positives, the study narrowed the 4.9 million sample to 53 stars. Analysis of these findings reveals several intriguing candidates. For example, one of the identified stars shows an infrared excess consistent with extreme debris disk characteristics, which could be mistaken for a technosignature. However, its older age calls into question existing models of planet formation, suggesting either an extended disk evolution or alternative processes. The implications of these discoveries are profound. If any of these infrared anomalies are indeed Dyson spheres, it would provide direct evidence of the existence of advanced extraterrestrial civilizations. However, the scientific community remains cautious. Natural phenomena such as dust clouds or the extreme debris disk can also provide similar infrared signatures. Therefore, each candidate requires careful follow-up observations to confirm or deny the presence of artificial structures. The controversy surrounding these findings emphasizes the difficulty distinguishing between natural and artificial sources of excess infrared radiation. Indeed, in general, the vast distances between Earth and potential candidates pose a severe problem. Many of the stars under study are thousands of light years away, making detecting and analyzing their infrared signatures extremely difficult. The farther away a star is, the fainter its signals are, and the harder it is to obtain good quality, accurate data. Some scientists argue that our current understanding of stellar and planetary dynamics is incomplete, And these anomalies may reveal new astrophysical phenomena rather than technosignatures. The search for extraterrestrial life has gripped humanity for centuries, evolving from philosophical speculation to a rigorous scientific approach. Today, scientists use various methods to detect signs of life beyond Earth, focusing on technosignatures and biosignatures. While technosignatures are indicators of advanced technological activity, including large-scale structures like Dyson spheres, unusual energy emissions, or artificial signals, biosignatures, on the other hand, are indicators of biological activity. They can range from detecting specific gases in a planet's atmosphere, such as oxygen and methane, to surface features indicative of life. Current and upcoming missions are crucial in detecting these subtle signs of life. For example, the James Webb Space Telescope can observe in the infrared, detecting the faint heat signatures of distant exoplanets and their atmospheres. This provides valuable data on potential conditions suitable for life. It has confirmed dozens of potentially habitable exoplanets in the past year alone. Another important initiative that goes shoulder to shoulder with JWST is TESS, the Transiting Exoplanet Survey Satellite, which aims to detect exoplanets by observing their transits through stars. TESS has already identified thousands of exoplanet candidates, many prime targets for further study with more powerful telescopes, such as Webb. Future missions promise to further enhance our ability to detect technosigns and biosigns. The proposed LUVOIR, Large UV Optical IR Surveyor, and HABEX, Habitable Exoplanet Observatory missions, are designed to directly image exoplanets and analyze their atmospheres. These next-generation telescopes will provide unprecedented clarity and sensitivity, allowing us to detect even the faintest sign of life or advanced technology. In addition to space observatories, ground-based telescopes, such as the Extremely Large Telescope and Square Kilometer Array, will play a crucial role. ELT, with its massive mirror, will be able to obtain direct images of exoplanets and study their atmospheres in detail. At the same time, SKA will focus on detecting radio signals from space that could indicate technological activity. The search for life is not limited to looking for existing civilizations. Scientists are also exploring the possibility of life in our solar system, focusing on moons such as Europa and Enceladus, which have subsurface oceans. Missions such as Europa Clipper and potential future missions to Enceladus aim to detect signs of microbial life in these hidden waters. As we continually refine our methods and technologies, each discovery, whether it confirms or disproves the existence of life, brings us closer to understanding our place in the universe. The journey is as important as the destination. It pushes the boundaries of science and ignites our collective imagination. And each innovation brings us closer to answering one of humanity's deepest questions. Are we alone in the universe? Imagine a colossal object 6 miles wide, hurtling through space at 12 miles per second toward Earth. And it's not science fiction. 66 million years ago, such an asteroid slammed into what's now the Yucatan Peninsula, forming the crater Chicxulub and triggering a mass extinction event. Today, our planet continues to be threatened by near-Earth objects. These include asteroids and comets, whose orbits bring them into our space neighborhood. NASA and other space agencies have made significant strides in tracking and understanding these potential threats, but the risk remains. Advanced technology is at work to monitor and mitigate these threats. From kinetic strikes to gravity tractors, humanity is developing strategies to protect our world from these stellar invaders. But what would happen if another Chicxulub-sized asteroid was on a collision course with Earth today? How prepared are we for such a catastrophic event? Join us to learn planetary defense, the history, science, and the future against such impressive threats. So 66 million years ago, an event occurred on Earth that was so catastrophic that it changed the course of life on the planet. The asteroid, about 6 miles in diameter, slammed into the Yucatan Peninsula in present-day Mexico, forming what we now call the Chicxulub crater. The immediate aftermath was nothing short of apocalyptic. The collision released energy equivalent to billions of nuclear bombs, caused forest fires and tsunamis, and threw huge amounts of debris into the atmosphere. The impact's most significant and long-lasting effect was the release of dust, soot, and sulfur aerosols into the atmosphere. These particles created a global cloud that blocked sunlight for an extended period, a phenomenon often referred to as impact winter. New research has shed light on the critical role of fine dust particles in this cataclysmic event. A study published in Nature Geoscience in October 2023 found that fine dust, particularly particles between 0.8 and 8 micrometers in diameter, played a significant role in abrupt climate change. The researchers collected 66 million-year-old rock samples from North Dakota, located an impressive distance from the impact site, which contained surprising amounts of these fine dust particles. These particles lingered in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the most severe. This long period of darkness led to a significant drop in global temperature, estimated at more than 18 degrees Fahrenheit, 10 degrees Celsius in the first year alone. As sunlight was blocked, photosynthesis stopped. Plants unable to produce food began to die out. This collapse of plant life had a cascading effect on the entire food chain. Herbivorous dinosaurs that relied on plants for their food, faced starvation. Consequently, the carnivorous dinosaurs that preyed on them also died. This chain reaction led to the extinction of about 75% of all species on Earth. Interestingly, the new study highlights the hitherto unnoticed impact of dust compared to soot and sulfur, which were previously thought to be the main culprits for the prolonged cooling period. The findings suggest that while soot and sulfur blocked sunlight more effectively, the sheer amount and persistence of dust had a profound and lasting impact. The study also provides insight into how some species managed to survive this dark period. Hibernating plants and animals had adaptations that allowed them to survive the prolonged lack of sunlight. However, the study casts doubt on the survival mechanisms of freshwater organisms, indicating that more research is needed to fully understand the specific mechanisms of death following a Chicxulub strike. So what are near-Earth objects? NEOs are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size, from small, harmless rocks to massive bodies capable of causing a massive catastrophe. Asteroids are the rocky remnants of the early solar system, mostly found in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate from the outer regions of the solar system and are composed of ice, dust, and rocky material. As they approach the Sun, they develop luminous comas and tails. The danger posed by these objects depends on their size and trajectory. Although most NEOs are too small to cause significant damage, some, such as the Chicxulub impactor, are capable of causing global catastrophes. To mitigate these risks, space agencies such as NASA and the European Space Agency have developed extensive programs to track and detect NEOs. Telescopes around the world are constantly scanning the sky, and cataloging objects that are approaching Earth's orbit. One of the key instruments in this work is the Wide Field Infrared Survey Explorer, which has been repurposed for the NEOWISE mission. Hundreds of near-Earth asteroids have been discovered and characterized using this space telescope. The role of artificial intelligence in detecting unobserved asteroids is becoming increasingly important. In May 2024, an AI-based algorithm known as Trackless Heliocentric Orbit Recovery, or THOR for short, detected more than 27,000 previously unobserved asteroids in archival telescope images. This artificial intelligence tool analyzes huge amounts of data, identifying and tracking objects with remarkable efficiency. It can process up to 1.7 billion points of light in a single telescope image, connecting them into asteroid trajectories. The Vera C. Rubin Observatory, due to begin operations next year, will further enhance our ability to detect NEOs. Equipped with advanced artificial intelligence software such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first few months of operation, doubling the current known population. While no near-Earth object is large enough to destroy the planet itself, asteroids of 1 mile or more in size can cause global catastrophes. For this reason, NASA has been tasked with detecting and tracking these large NEOs. As of 2021, NASA has detected over 90% of the largest objects, ensuring that none of them pose an immediate threat to Earth. However, smaller objects, while not as catastrophic on a global scale, can still cause significant regional damage. Take, for example, Apophis, named after the Egyptian god of chaos and destruction. It's a near-Earth asteroid that's captured the attention of scientists and the public. Discovered in 2004, this 1,000-foot wide or 304-meter wide asteroid initially caused concern because of calculations suggesting a possible collision with Earth in 2029. However, further observations have ruled out this possibility, confirming that Apophis will pass our planet safely. On April 13, 2029, Apophis will make an incredibly close approach to Earth, passing within 30,000 miles or 48,300 kilometers of our planet. By comparison, this distance is closer than the orbits of our few high-altitude satellites. This close pass provides a unique opportunity for scientific observations and research. During the flyby, the asteroid will become visible to the naked eye in some regions, appearing as a bright, moving point of light. This rare event will allow scientists to study its size, shape, and composition in unprecedented detail. NASA's Goldstone Deep Space Communications Complex in California will play a crucial role in observing Apophis. Using radar, scientists hope to gather detailed information about the asteroid's surface features and rotation. In addition, the NEOWISE mission can provide additional observations by focusing on Apophis's surface roughness and composition. These data are invaluable as they'll help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, will make a close approach to Apophis during its shortest flyby. The mission's goal is to study the asteroid up close, providing detailed observations that ground-based telescopes cannot achieve. OSIRIS-APEX will collect data on the composition and surface structure of Apophis, as well as any changes that occur as it passes near Earth. The spacecraft's instruments will help determine the asteroid's internal composition, which will also contribute to our broader understanding of the formation and evolution of the solar system. The close passage of Apophis has also attracted the attention of international space agencies. Teams from all over the world plan to observe and study the asteroid using ground and space telescopes. As part of the Neolite project, researchers from the Julius Maximilians Universität in Würzburg have proposed several concepts for small spacecraft that could accompany Apophis during its flyby. One proposed mission includes a small satellite that would follow Apophis for 2 months, acquiring high-resolution images and measurements. Another concept combines a small satellite with the European Space Agency's planned Ramses mission, which would provide extensive scientific observations. Although the asteroid poses no immediate threat to Earth, its close approach in 2029 presents a great scientific opportunity. Studying this asteroid up close will greatly improve our planetary defense strategies. To protect Earth, scientists have developed several planetary defense mechanisms, each designed to prevent potential collisions. One of the main methods is the kinetic impact strategy. It involves sending a spacecraft that will collide with an asteroid at high speed, altering its trajectory. This method relies on momentum transfer to move an asteroid into a safer orbit. NASA's 2022 mission Double Asteroid Redirection Test, or simply DART, was the first test of this method. The DART target was a small lunar satellite, Dimorphos, orbiting a larger asteroid, Didymos. As a result of the collision, Dimorphos's orbit was successfully altered, providing valuable data for future missions. Another proposed method is the gravity tractor. This method uses the gravitational pull of the spacecraft to slowly change the trajectory of the asteroid over time. By maintaining a stable position near an asteroid, the spacecraft's gravity can gradually alter the object's trajectory. Although this method's still theoretical and hasn't been tested in space, it is a promising approach for dealing with potential threats identified in advance. In extreme cases, however, nuclear explosions could be used to deflect or destroy an asteroid. In this approach, a nuclear device is at a safe distance from the asteroid, vaporizing part of its surface and creating a recoil effect that moves the asteroid off course. However, this method is controversial because of the potential risks and legal implications of using nuclear weapons in space. To prepare for potential asteroid impacts, international space agencies regularly conduct simulations and drills. These exercises help hone detection, tracking, and deflection strategies. Planetary defense is a global issue that requires cooperation and coordination among countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The exercise simulated the detection of a fictional asteroid on a collision course with Earth, allowing participants to practice their response strategies. As we continue to develop and refine our planetary defense strategies, international cooperation, and technological advances, they'll all play key roles in protecting our world from space-based threats. These cooperative efforts are essential, especially as we learn more about the diverse nature of the objects that threaten us. Asteroids and comets are often viewed as different celestial bodies. Asteroids are like the rocky remnants of the early solar system, mostly from the belt between Mars and Jupiter. Comets, on the other hand, are aliens from the outer reaches of our system and are composed of ice, dust, and rocky material. However, there are also rare objects that blur the boundaries between these two categories, exhibiting characteristics of both. One such object is QN-173, discovered in 2005. This unique celestial body orbits like an asteroid, but behaves like a comet. Unlike ordinary asteroids, which are inert, QN-173 exhibits comet-like activity by ejecting dust and developing a long, thin tail as it approaches the Sun. QN-173 orbits the Sun every 5 years, spending most of its time in the outer part of the asteroid belt. However, as it approaches the Sun, it shows increased activity, similar to a comet. This duality makes 2005 QN-173 an interesting object for astronomers. In the summer of 2021, astronomers using the Asteroid Terrestrial Impact Last Alert System in Hawaii observed an object displaying a comet-like tail. Further observations by Lowell Observatory and the Zwicky Transient Facility confirmed this activity. The 450,000-mile or 720,000-kilometer-long tail suggests that the object is covered in icy material that sublimates when heated by the Sun. It's this process that turns the ice directly into gas, releasing dust and creating the characteristic tail. Interestingly, the narrowness of the tail indicates that the dust particles barely leave the core at extremely slow velocities. This presents a mystery to scientists, as such slow velocities would not normally allow dust to escape the asteroid's gravity. One hypothesis is that the rapid rotation of the core may contribute to the dust ejection. In addition to unique objects such as 2005 QN-173, many other near-Earth objects pose a potential threat to our planet. The European Space Agency maintains a comprehensive risk list, cataloging objects with a non-zero probability of colliding with Earth. The list contains detailed information on the size, velocity, and collision probability of each object. It currently contains over 1,600 targets. The list of risks is sorted by the Palermo scale, a logarithmic scale that assesses the risk of collision based on an object's size, speed, and probability of collision. Objects with higher values on the Palermo scale pose a greater potential threat. Statistical analysis of these potentially hazardous asteroids shows that while most NEOs pose minimal risk, there are a few objects that require close observation. For example, the size and velocity of an asteroid have a very significant impact on its probability of impact and potential damage. Large asteroids, usually over 1 kilometer in diameter, are of particular concern because of their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked more than 90% of these large objects, ensuring that none of them pose an immediate threat to Earth. Smaller objects, while not as catastrophic, can still cause significant regional damage. Events such as the Chelyabinsk meteor in 2013 and the Tunguska event in 1908 demonstrate the potential danger of small asteroids. As we continue to discover and track NEOs and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the Moon, Io. unlike any other orbiting the mighty Jupiter. Shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles. Given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. Imagine a particle so elusive that trillions pass through you every second but leave no trace. A particle born in the fiery hearts of stars, in the cataclysmic collapse of supernovae, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space, carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we finally learn to listen to their whispers? Diving into the realm of these ghostly particles, we go where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. The neutrino story begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was a time when the universe was revealing its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem. In beta decay, a type of radioactive decay observed in atomic nuclei, energy seemed to disappear. This disappearance contradicted the principle of conservation of energy, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried away by an undetectable particle? He tentatively named this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory describing this elusive particle and cementing its place in the scientific lexicon. Let's travel back to the Cold War era, a time when science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the center of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not just about military might. It extended to the realm of science, where both sides sought breakthroughs that could give them an advantage. One such story is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some conducted deep underground in abandoned mines or remote locations, where scientists were trying to catch these ghostly particles. Neutrinos, while among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that for a long time it was thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it were not there. Trillions are passing through you right now, completely undetected. 3 types or flavors of neutrinos are known: electron, muon, and tau neutrinos. Each is associated with a corresponding charged particle: electron, muon, and tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery because it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can move between these mass states, resulting in a change in flavor. This discovery not only won the 2015 Nobel Prize in Physics, but also pointed out gaps in the standard model, changing our understanding of fundamental physics. Neutrinos are also key players in some of the most dramatic processes in the universe. At the heart of a star, nuclear reactions generate huge numbers of neutrinos, which then leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to fly out of a dying star, signaling the start of a supernova. These particles provide crucial information about the processes taking place in the core, long before the light can escape. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova explosion. During this cataclysmic explosion, an enormous number of neutrinos are produced, orders of magnitude greater than the energy emitted by light. These neutrinos leave the supernova almost instantly, spreading through space, and some of them eventually reach Earth, giving a glimpse into these distant, violent events. There's also speculation that neutrinos may be linked to one of astrophysics' biggest mysteries: dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino, that does not interact with any known fundamental force other than gravity, may make up dark matter, the invisible mass that makes up most of the universe's matter. Although this remains an area of intense research, the possibility that neutrinos could unlock the secrets of dark matter emphasizes their importance to our quest to understand the cosmos. So the hunt for high-energy neutrinos has taken scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica stands the Ice Cube Neutrino Observatory, scanning the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events that are still cloaked in mystery. Recent research has begun to peel back the layers of this mystery, pointing to active galactic nuclei, or AGNs, as significant sources of these high-energy neutrinos. AGNs are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases huge amounts of energy, often forming jets of high-speed particles. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a likely source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the galaxy's core, where a supermassive black hole is hidden behind thick layers of dust and gas. This discovery disproved the popular belief that such neutrinos can only be emitted by galaxies with bright jets, such as blazars. The surprises didn't end with NGC 1068. Further studies revealed two more galaxies, NGC 4151 and NGC 3079, as potential sources of high-energy neutrinos. The findings strongly suggest that the environment around supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of where high-energy neutrinos come from. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to push the boundaries of our knowledge even further. In Japan, the Hyper Kamiokande is poised to become a leader in neutrino detection. This huge underground detector, located in a cave specially dug for the purpose, will be filled with 260,000 tons of ultraviolet water. The goal is to capture fleeting flashes of Cherenkov radiation produced when neutrinos interact with water molecules, a technique honed over decades of Japanese research. Meanwhile, in the US, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will utilize a state-of-the-art time projection camera in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map neutrino properties in great detail. Although both the Hyper Kamiokande and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K is based on proven technologies and aims at mass data collection. DUNE, on the other hand, relies on innovative technologies that can reveal new aspects of neutrino behavior. The stakes are high. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which may explain why the universe is composed mainly of matter rather than antimatter. Charge parity violation, CP violation, could be the key to solving this cosmic mystery, and Hyper-K and DUNE are designed to find it. By comparing the oscillations of neutrinos and their antimatter, antineutrinos, as they pass through space, these detectors can show whether there's a fundamental difference in the behavior of matter and antimatter. But the race to find CP violation is also a race against time. Hyper Kamiokande is expected to begin collecting data as early as 2027, which could give it an edge over DUNE, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, providing a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations. And nowhere is this more apparent than in the study of neutrinos. These elusive particles, which have almost no interaction with other matter, have properties that push the boundaries of our understanding. One of the most serious challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to be massless, but the observation of neutrino oscillation, when neutrinos change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model. But that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model. They suggest the possible existence of a new type of neutrino, the sterile neutrino. Now, we've already mentioned this in passing, but here's the gist of it. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos interact only through gravity. This makes them even more difficult to detect, but their existence may well explain several mysteries in physics. If sterile neutrinos are shown to exist, they'd not only call into question the completeness of the Standard Model, but would open the door to entirely new physics. This would require extending the model to include these new particles, potentially leading to a more unified theory of the fundamental forces. Neutrinos may also provide clues to another profound mystery, the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates, and antimatter is rare. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos do break this symmetry, this could later explain why there is more matter than antimatter left after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence for CP violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185-mile, 300-kilometer journey across Japan to the Super Kamiokande detector. For nearly a decade, researchers have noticed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may indeed behave differently. This potential CP violation in neutrinos could be the missing piece to explain why the universe is made up mostly of matter. However, the current results, while promising, are not yet conclusive. The level of statistical significance required to recognize a discovery in particle physics is 5 sigma. The T2K results have only reached about 3 sigma, and this means that although the evidence is strong, it's not absolute. To truly confirm the CP violation in neutrinos and unlock the secrets of antimatter rarity, scientists are turning to the next generation of neutrino detectors. Hyper-K in Japan and DUNE in the US are poised to take this research to the next level. These massive detectors will collect many times more data with greater accuracy, potentially reaching the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science: why there is something rather than nothing. The study of neutrinos, once considered an obscure branch of physics, may ultimately hold the key to understanding the very fabric of our reality. To answer some of physics' deepest questions, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or CATRIN, in Germany. The CATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny neutrino mass. By analyzing the energy of the electrons emitted in this decay, CATRIN aims to set an upper limit on the neutrino mass, pushing the boundaries of discernibility. CATRIN has already made significant progress, setting an upper limit on the neutrino mass of 0.8 electron volts with sensitivity down to 0.2 electron volts. However, this may not be sufficient to determine the true neutrino mass, which maybe even smaller. This realization has sparked a global develop alternative methods and experiments that could surpass the capabilities of Katrin. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays via electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected by extremely sensitive equipment. Experiments with holmium-163 have already demonstrated highly accurate energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the Project 8 experiment, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could surpass the limit set by cosmological studies and provide crucial data on the true mass of neutrinos. The quest to understand neutrinos is not confined to one country or continent. It's truly a global endeavor. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration across borders. As we await the first signals from Japan's Hyper-K, which is already taking shape in a newly dug cave, and await news from Dune, nestled deep in an old South Dakota gold mine, the next chapter in our understanding of the universe is just beginning. Stay tuned as we journey through the frontiers of science, making one discovery at a time. Beyond the reach of traditional microscopes and within theoretical physics lies a frontier not so much of remoteness as of possibility and understanding. This frontier is challenged not by physical barriers or vast distances, but by the depth of its implications and the invisibility of its scope. Welcome to the quantum realm, where the building blocks of technology and reality behave quite differently from anything we have encountered in our macroscopic world. Quantum mechanics is a phrase that excites the intellect and baffles the mind with its strangeness. Here, particles can exist in several places at once. They can spin in opposite directions at the same time. They can be entangled in the vastness of space, acting in concert with no apparent connection. These bizarre behaviors are at the heart of a technology that could revolutionize our world. Quantum computing. In the heart of this technological storm lies a concept so revolutionary and yet so elusive that it challenges our very perception of information and reality. By traveling the quantum frontier, we enter a space where information is not just processed, but exists in states that defy classical logic. Here, quantum bits, or qubits, can store many possibilities at once, compared to the simple bits of today's digital devices. But how to preserve information in a system that loses its essence at the slightest interaction with the environment? And scientists may have some answers to that question, because quantum mechanics does more than just redefine computing. It encourages us to rethink the cosmos, intertwining with the fabric of space and time in enigmatic phenomena such as black holes. These cosmic anomalies are not mere objects, but the key to understanding the quantum puzzles that hold the secrets of the universe's information storage and retrieval systems. Join us on our expedition, an expedition to the frontier of quantum mechanics exploration that may ultimately redefine the meaning of computing, data protection, curing disease, and perhaps understanding the very fabric of reality itself. So you and I are gradually entering a new era of computing that transcends the binary landscape of classical computing, where data is processed as a straight series of zeros and ones. In contrast, quantum computing works with qubits, which can embody zeros, ones, or both at the same time, utilizing special properties of quantum mechanics to perform complex computations at unprecedented speeds. However, the quantum world is as fragile as it is powerful. One of the main challenges in developing quantum computers is creating and maintaining quantum memory. You see, unlike classical digital memory, which can reliably store information and retrieve it at will, quantum memory is extremely fragile. Any interaction with the external environment can cause quantum information, known as quantum states, to decohere, that is, erase the stored data. This is like trying to hold a spinning coin on its edge. This susceptibility stems from the fundamental nature of quantum memory. It's not simply a matter of storing data, but of preserving complex quantum states, which are the basis of the potential of quantum computing. Herein lies the paradox at the heart of quantum computing, the no-cloning theorem. This theorem is a unique rule of the quantum world and states that it's impossible to create an exact copy of an unknown quantum state. In the everyday world, if you want to prevent data loss, you can make copies of it. But in quantum computing, it's impossible to make an exact copy of a qubit containing unknown information. This rule is a serious obstacle because it means that traditional methods of data protection and error correction, such as backups, simply don't work. Engineers and physicists are now tasked with developing innovative strategies to combat these problems. They're using quantum error correction techniques that involve entangling qubits, linking them together in complex ways, and allowing the system to detect and correct its own errors without having to directly measure the quantum state. These methods don't just preserve information, they preserve the very essence of quantum behavior. But how can the very gravity wells where not even light can penetrate and quantum computing be related, you might ask? The intriguing connection between black holes and the burgeoning field of quantum computer science begins with one deep mystery they share in common. Stephen Hawking and Jacob Bekenstein, two titans of theoretical physics, once proposed groundbreaking ideas about black holes that have profound implications for modern quantum computing. In a thought experiment, Hawking hypothesized the black hole information paradox, which poses a profound dilemma. What happens to information when it falls into a black hole? Does it disappear forever, or does it persist in some form? This question is analogous to quantum computing's problems with data integrity and loss. Just as information must be preserved when it crosses the event horizon of a black hole, quantum information must be preserved in the unstable environment of a quantum computer. So how much information can a black hole store? Bekenstein in turn presented the concept that the entropy of a black hole, in fact its information content, is proportional not to its volume, as one might expect, but to the area of its event horizon. But how can a surface store information, you may ask? After all, you need some kind of structure. You need atoms or something else that can store bits of information. Well, it turns out that you can calculate that a black hole stores information in bits. The amount of information is equal to the surface area of the event horizon in Planck square units. Planck units are the smallest measurable scales in the cosmos. These units, named after Max Planck, mark the limits beyond which classical theories of gravity and space begin to break down and quantum effects become dominant. Planck units serve as a bridge in our understanding of quantum and cosmological scales, providing a framework that helps us quantify the universe in the most minuscule dimensions imaginable. So why is the information content of a region of space equal to the surface area surrounding that region and not its volume? Consider this analogy to better understand the unconventional way information is stored in a black hole. Imagine that your room is not just a library, but a magical library where your entire collection of books can be encoded simply on the wallpaper that covers the walls. Here, instead of measuring the volume of the room to determine how much it can hold, we look at the surface area of the walls. This radical idea reflects how black holes store information, but not in their vast void, but on their outer surface, at the event horizon. And this leads us to the holographic principle, which may seem like science fiction, but it is a serious scientific theory inspired by the thermodynamics of black holes. A hologram, colloquially speaking, is a flat surface that contains all the data needed to display a three-dimensional image. If you apply this to the universe, a startling possibility arises. Everything you see around you, from your cup of coffee to the stars in the sky, could be a projection of information encoded on a distant two-dimensional surface. The Won-Maldacena model, known as the Anti-de Sitter Conformal Field Theory Correspondence, or ADS-CFT, goes further. It proposes that the type of universe described by Einstein's theory of gravity, negatively curved and seemingly limitless, could be equivalent to a gravity-free quantum field theory defined at the boundary of that space. Essentially, it's as if there were a boundary at the end of the universe that contained a two-dimensional description of all three-dimensional events occurring in it. This revolutionary idea suggests that our understanding of space and time, however intuitive it may seem, may be an emergent phenomena from a deeper, more fundamental reality. The implications for quantum computing are profound. By mimicking the natural holographic data storage observed in black holes, engineers will be able to create quantum systems that are both stable and powerful, capable of performing computations impossible for classical computers. As we move closer to mastering quantum computing, its impact on our future is becoming increasingly clear and promising. This technology doesn't just increase the speed of data processing, it expands our ability to solve problems previously thought unsolvable. Cryptography, medicine, and space exploration are just the beginning. In the field of cryptography, quantum computing is a double-edged sword. On the one hand, they pose a significant threat to existing encryption methods. Traditional security protocols rely on the complexity of factorizing large numbers, for which quantum computers are exceptionally well suited. This capability means that most existing encryption methods can become obsolete over time, leaving data vulnerable, from your personal correspondence to access to your bank account. However, this same ability opens up the potential for quantum cryptography, which can provide a level of security that's fundamentally unbreakable. Quantum key distribution uses the principles of quantum mechanics to create secure communication channels. Unlike traditional keys, any attempt to eavesdrop on quantum keys changes their state, thereby revealing the presence of an attacker. This method could revolutionize the transmission of sensitive information, making our data secure against even the most sophisticated attacks. In medicine, the impact of quantum computing could be revolutionary. The ability to accurately model molecules and biological processes opens new horizons in drug development. Currently, the development of new drugs is a long and expensive process, often taking more than a decade. Quantum computers can significantly speed up this process by predicting the properties of complex molecules and their interactions with the human body more accurately than ever before. One interesting example is the use of quantum computing to develop treatments by modeling the human lung on a chip. This innovative approach, developed by a Swiss startup, uses quantum computing to model human lung cells on a microchip. These cells can be mechanically activated to mimic the behavior of a real lung, allowing researchers to observe how drugs interact with human tissue in real time. Imagine a world in which we can model the human body in minute detail on quantum computers. creating digital twins that doctors can use to test treatments tailored to each patient. This approach could not only speed up the development of new drugs, but also improve their efficacy and safety many times over. It represents a shift towards more personalized medicine, where treatments are optimized for each patient's unique genetic characteristics. Beyond healthcare, quantum computing also promises to revolutionize energy efficiency across sectors. Its ability to solve complex logistical problems and optimize systems can lead to more efficient use of resources. For example, quantum algorithms have already improved cargo movement at the Port of Los Angeles, increasing throughput and reducing energy consumption. Space exploration can also benefit greatly from quantum computing. Navigating vast expanses of space requires processing vast amounts of data for trajectory alignment, system diagnostics, and life support management. Quantum computers could improve the ability of spacecraft to perform these tasks autonomously, making deep space missions more feasible. In addition, quantum technologies can improve our ability to predict and understand space weather, protecting astronauts from harmful radiation, and preserving critical satellite infrastructure. Research into black holes and quantum mechanics is not just a theoretical fad. It's shaping the very tools we expect to revolutionize our future. The insights gained from studying these cosmic mysteries are helping to inform and advance algorithms that will one day be able to manage our data, cure our diseases, and even guide our research into the uncharted reaches of the cosmos. So, quanta, in simple terms, are the smallest possible units of any physical property involved in an interaction, such as energy or matter, such as particles and photons. In classical physics, everything seems smooth and continuous. But at the quantum level, things like energy move in tiny, discrete packets, i.e. quanta, and that's why there are quite a few different methods of quantum computing, each exploring unique approaches to using these tiny units to generate enormous computing power. One of the leading techniques in current quantum computing research involves superconducting circuits. Companies such as Google, IBM, and Rigetti are investing heavily in this technology, which uses supercooled circuits to minimize energy loss and maximize efficiency. These circuits operate at temperatures near absolute zero, allowing quantum states to persist long enough to perform complex computations. Another well-known method uses trapped ions and qubits. Companies such as IonQ and Quantinuum use this technique, where ions are held in space using electromagnetic fields and manipulated with lasers to perform quantum operations. This method boasts longer coherence times, meaning that quantum states remain stable for longer periods of time, although the speed of operation is generally slower compared to superconducting circuits. Photonic quantum computing is also gaining momentum with qubits encoded using photons, particles of light. This approach, promoted by companies such as Xanadu and startups affiliated with academic groups, operates at room temperature and uses the properties of light to perform quantum computing. Recent advances include Xanadu's development of a Borealis chip, which uses a novel method of manipulating groups of photons to gain quantum advantages. In turn, topological quantum computing, which has emerged from a more theoretical framework, offers a new approach to utilizing quasi-particles, particles that arise from interactions within a material. Microsoft's been a key player in this field, exploring ways to create and manipulate these quasi-particles to create qubits that are naturally immune to external perturbations, potentially solving the problem of quantum decoherence. In addition, one quite revolutionary approach to quantum computing is rapidly gaining momentum. This new method, using atoms held in optical tweezers, represents a significant leap forward in our quest to harness quantum mechanics for computing power. Let's take a closer look at this innovative. It has the potential to revolutionize the field. Optical tweezers, a tool that uses focused laser beams to capture and manipulate particles, are nothing new in physics, but their application in quantum computing is a new and rapidly developing frontier. By using lasers to capture individual atoms, scientists create qubits that are less susceptible to interference and easier to control than traditional methods. This technique is based on the unique properties of atoms. Being small and electrically neutral, they naturally avoid mutual interference that interferes with other types of quantum bits. This reduction in noise and interference is crucial to maintaining the coherence of quantum information, which is an ongoing challenge in quantum computing. A recent breakthrough in February this year involved the use of micro-lens arrays, which allow a significant increase in the number of atoms that can be manipulated simultaneously. These arrays allow thousands of atoms to be precisely arranged in regular order, each held in place by its own microscopic laser trap. Researchers have successfully used this technique to arrange more than 1,000 atoms with remarkable precision. And these atoms are not just statically held, they are dynamically controlled, ready to perform complex quantum operations. The term supercharging accurately describes the improvement this method brings to quantum computing. By aligning two layers of micro-lens arrays and superimposing laser traps on them, scientists create a dense grid of atomic qubits. This arrangement not only increases the initial number of qubits, but also improves their overall stability and homogeneity. Each atom trapped by this method can potentially serve as a quantum bit. The precision of this approach allows each qubit to be individually addressed and manipulated, opening the way to complex and large-scale quantum algorithms that were previously unattainable. When this new method's compared to existing technologies such as superconducting qubits and ion traps, the atoms in tweezers approach offers significant advantages in scalability and error reduction. Its ability to scale rapidly to thousands of qubits makes it a formidable competitor to better-known technologies. Looking ahead, the potential to scale this technology to 100,000 atoms and beyond is not just optimistic speculation, but a very realistic goal. Achieving this scale could bring quantum computing closer to commercial viability, allowing complex problems, from cryptography to materials science, to be solved. As we conclude our journey through the quantum frontier, we find ourselves at a pivotal moment where quantum computing is moving from theoretical research to practical applications. The X Prize Quantum Applications Competition epitomizes this transition, presenting a challenge with a significant $5 million incentive to spur innovations that apply quantum computing to real-world problems. Over the next 3 years, teams from around the world will explore and demonstrate how quantum technologies can revolutionize healthcare, material science, energy, and other fields. This initiative not only accelerates the development of quantum technologies, but also emphasizes the potential of quantum computing to solve humanity's most urgent problems. By pushing the boundaries of quantum computer capabilities, X Prize aims to stimulate the transition from experimental quantum applications to everyday tools, making the fields of quantum mechanics accessible and useful to society at large. In the 21st century, humanity finds itself at a crossroads at a moment in history when we can see the stars, but not yet touch them. Born in the era between exploring our own planet and the possibility of reaching other worlds, we stand on the threshold of an extraordinary journey. It's not just about rockets or physics, but about our survival and our place in the universe. Imagine a future in which Earth faces an existential threat, a catastrophic collision with an asteroid, a climate collapse, or something completely unforeseeable? Our solution? Build generation ships. Colossal spaceships that serve as floating cities where multiple generations are born, live, and die while traveling to another star, to a new home. Einstein's special theory of relativity tells us that traveling faster than light is impossible. However, space is within our reach, even at a speed that is only a fraction of the speed of light. Generation ships traveling at a significant fraction of light speed could travel vast distances between stars. With technology such as matter-antimatter engines, compact fusion drives, and even black hole propulsion, what seems like science fiction could become a reality. But these ships are not just vessels. They are lifeboats for humanity. They must sustain life for centuries, perhaps millennia, facing the challenge of space travel, genetic diversity, and mental health. Each ship will be a microcosm of Earth, with its social structures, cultural heritage, and daily challenges. What would it take to build such a ship? How can its inhabitants survive and thrive? Join us as we delve into the intricacies of interstellar travel without exceeding the speed of light. Today, we'll try to unlock the secrets of how humanity can one day travel to the stars, but not in an instant, but through generations. Planning for interstellar travel is not only about technology, but also about predicting why such travel might become necessary. Foreseeable threats to humanity's survival may force us to seek refuge outside our solar system. Understanding these threats will help us prepare for possible future scenarios that could force humanity to embark on such an extraordinary journey. One of the most immediate threats comes from space itself: comet impacts. Throughout Earth's history, collisions with comets and asteroids have caused mass extinctions and major climate shifts. A strong enough collision could make Earth uninhabitable, forcing us to seek a new home among the stars. Another serious threat is climate collapse. Human activity has already led to significant changes in our climate: rising temperatures, melting polar ice caps, and increasingly severe weather events. If these trends are not controlled, Earth could become hostile to human life, making searching for habitable exoplanets a top priority. Technological progress, while bringing enormous benefits, also carries significant risks. Advances in artificial intelligence, biotechnology, and autonomous systems could lead to scenarios where humanity faces a threat from its own creations. Uncontrolled AI or engineered pathogens could become existential risks, leading to the need to establish human colonies on distant worlds as a defense of our species. In search of a new home, Proxima Centauri b is a prime candidate. Located just 4.24 light-years away in the Alpha Centauri system, it is the closest known exoplanet that's in the habitable zone of its star. As many know, this zone, often referred to as the Goldilocks zone, is the area around a star where conditions may be optimal for the existence of liquid water, an essential ingredient of life for humanity. Proxima Centauri b was discovered in 2016 and has been the subject of intense study ever since. It orbits a red dwarf star that's smaller and colder than our Sun, meaning the planet would have to be much closer to its star to be in a habitable zone. Proximity, while favorable for retaining heat, also exposes the planet to flares and radiation, which must be considered when planning human habitation. Current research indicates that the planet has a mass similar to Earth's and may have a rocky surface. However, much about it remains unknown, including the composition of its atmosphere and the presence of liquid water. Future missions and observations will be needed to collect more data and assess its suitability for life. Sending a spacecraft to our nearest neighboring star involves not only covering the distance, but also ensuring that the distance is suitable for human life. This requires a multifaceted approach that includes robotic probes and telescopes to gather detailed information about the planet's environment. These missions will help determine the feasibility of establishing a human colony and the preparations necessary for long-term survival. Proxima Centauri b was chosen as our target because of its relative proximity and potential habitability. However, reaching and inhabiting the distant world will be a monumental task requiring an unprecedented level of planning, innovation, and collaboration. The dream of exploring the stars has always been tempered by the harsh realities of physics and time. Traditional concepts of space travel, where one crew sets off and reaches their destination within their lifetime, seem increasingly impractical when it comes to the vast distances between the stars. This is where the concept of intergenerational ships come into play, a bold and innovative solution to the problem of long-distance space travel. Generational ships, also known as intergenerational or generation ships, are designed to keep people alive for centuries or even millennia. These ships are self-sustaining ecosystems with not only one crew on board but all of their descendants. Life on a generational ship is designed to mimic a small self-contained world with living quarters, food production, water recycling, and social systems. The concept is simple, yet profound. As the original crew ages and eventually passes away, their children and their children's children continue the mission. This life cycle ensures that for many generations, the ship will continue its journey, and each new generation will be trained and prepared to maintain the ship and eventually reach its destination. This approach to space travel requires careful planning and robust systems to ensure that the inhabitants survive and thrive. Every aspect of life must be carefully considered, from genetic diversity to ensure a healthy population, to cultural and educational programs that preserve and pass on vital knowledge and skills. Einstein's special theory of relativity presents a serious problem for traveling faster than light. According to this theory, as objects approach the speed of light, their mass increases and they require exponentially more energy to continue accelerating. This effectively makes traveling faster than the speed of light impossible with our current understanding of physics. Generational ships offer a practical solution within the framework of Einstein's theory. By accepting the duration of space travel and planning for generations of life aboard such ships, humanity can aspire to distant stars. Such an approach recognizes the limitations imposed by the theory of relativity, while at the same time supporting the resilience and adaptability of the human spirit. Traveling to the stars requires overcoming significant challenges, not the least of which is the vast distance between celestial bodies. To make interstellar travel feasible within a human lifetime, we have to take a closer look at the advanced propulsion techniques and the intriguing phenomenon of relativistic time dilation. Relativistic time dilation is a consequence of Einstein's special theory of relativity. When an object approaches the speed of light, time on board is slowed down compared to the time experienced by an observer at rest. This means that for a spacecraft traveling at a significant fraction of the speed of light, the travel time of the crew will be shortened compared to those who remain on Earth. For example, if a ship could travel at 90% of the speed of light, time dilation would cause 1 year aboard the ship to be equivalent to more than 2 years on Earth. Because of this effect, interstellar journeys stretching over decades or centuries may seem shorter to the crew, although they do not shorten the actual distance. Several advanced propulsion methods have been proposed to achieve the high speeds required for interstellar travel. Each method has its own set of problems and potential advantages. For example, antimatter propulsion involves the annihilation of matter and antimatter with the release of enormous amounts of energy. This reaction releases energy much more efficiently than chemical rockets. potentially allowing spacecraft to reach significant fractions of the speed of light. However, producing and storing sufficient antimatter remains a major technical hurdle. On the other hand, compact fusion reactors use nuclear fusion, the same process that powers the sun, to produce energy. By combining light atomic nuclei, such as hydrogen, with heavier nuclei, these reactors could provide sustained and powerful thrust for spacecraft. While controlled fusion technology is promising, it's still under development, and building a compact and reliable reactor suitable for spaceflight is another major engineering challenge. Black hole propulsion is a more speculative concept that involves harnessing the enormous gravitational energy of a black hole to propel a spacecraft. The idea is to create a small artificial black hole and harness the energy of the Hawking radiation it emits. Theoretically, this method could provide continuous and powerful acceleration, but the technology to create and control artificial black holes is still in the realm of something fantastic, far beyond our current capabilities. However, the problems don't end with thrusters. Traveling at near light speed is fraught with many dangers. One of the main ones is the threat posed by interstellar particles. At these high speeds, even tiny particles can cause significant damage in a collision. Spacecraft must be equipped with advanced shielding to protect against these high-energy collisions. Radiation is another serious hazard. High-speed space travel exposes the crew to intense cosmic radiation that can have deleterious health effects. Effective radiation protection and possibly even medical intervention will be a necessity to keep the crew healthy during long-duration missions. Maintaining the structural integrity of the spacecraft over the long term is also critical. The stresses and strains of high-speed flight can weaken materials over time, requiring advanced construction techniques and regular maintenance to keep the spacecraft safe and functional throughout the voyage. Despite these formidable challenges, the pursuit of interstellar travel drives human ingenuity and ambition. By researching and developing advanced propulsion techniques and overcoming the dangers of high-speed travel, we're taking crucial steps toward reaching for the stars and expanding our presence in space. Choosing the right propulsion system for interstellar travel is one of the most important decisions in mission planning. The propulsion system determines the speed, duration, and feasibility of the mission, so it's important to explore both best practices and traditional methods. One promising approach is to scale up the traditional propulsion technologies. NASA's Parker Solar Probe uses a combination of chemical propulsion and gravitational assists to achieve unprecedented speeds. The probe is traveling at more than 430,000 miles per hour, which is approximately 0.064% of the speed of light and makes it the fastest man-made object to date. Its propulsion system is based on hydrazine thrusters, powered by solar energy, which showed the potential of using existing technology for high-speed space travel. Gravitational assists, or slingshot maneuvers, use the gravity of planets or other celestial bodies to increase the speed of a spacecraft without expending additional fuel. By carefully planning a trajectory, a spacecraft can gain significant speed, reducing travel time over vast distances. This technique, while insufficient by itself for interstellar travel, can be an important component of a multi-stage propulsion strategy. Scaling up these traditional technologies involves developing more efficient thrusters and larger amounts of fuel. Another promising area is innovation in ion thrusters, which use electric fields to accelerate ions and create thrust. Ion thrusters are highly efficient and can operate for long periods, making them suitable for long-duration missions. The combination of these advanced conventional methods could be a practical solution for the initial stages of interstellar travel. For faster travel, we must consider more advanced propulsion methods, such as nuclear propulsion. One of the most intriguing concepts in this category is the Orion project, first proposed in the 1950s. This method involves a series of thermonuclear explosions behind the spacecraft, each of which creates a powerful thrust to propel the spacecraft forward. The Orion project uses a massive pusher plate at the rear of the spacecraft, designed to absorb shock waves from explosions and convert them into forward momentum. By repeating this process in a controlled manner, the spacecraft will be able to reach significant fractions of the speed of light, drastically shortening the flight time to nearby stars. Although the concept is theoretically sound, many technical and safety problems still have to be solved. Controlling the timing and directions of explosions requires precise design, and the spacecraft in turn must be designed to withstand enormous loads. In addition, the environmental impact of launching such a vehicle from Earth must be carefully considered, which may also require space launch platforms. Another fusion engine concept is the Daedalus project, which involves using fusion reactions to propel a spacecraft. This method involves the use of small pellets of fusion fuel, such as deuterium and helium-3, which are ignited by electron beams to create a constant thrust. The Daedalus project aims to reach speeds of up to 12% of the speed of light, which would make it possible to travel to the nearest stars within a human lifetime. Fusion propulsion offers a more controllable and potentially safer alternative to the Orion method. However, the technology to build reliable and efficient fusion reactors for spaceflight is still under development. Significant advances in fusion research and engineering are needed to make this approach viable for interstellar missions. Choosing the right propulsion system is a balance between feasibility, safety, and performance. Traditional methods, such as those used in the Parker Solar Probe, offer practical short-term solutions, while advanced fusion propulsion concepts such as the Orion and Daedalus projects promise the potential for faster and more ambitious interstellar travel. Ensuring the survival and health of the crew over multiple generations is a cornerstone of generational ship planning. One of the most important aspects is maintaining genetic diversity, which is necessary to prevent inbreeding and genetic diseases that could jeopardize the mission. To solve the problem of genetic diversity, scientists use Monte Carlo simulations. These models use statistical methods to simulate and predict genetic variability over many generations. By introducing various parameters such as initial population size, mutation rates, and reproductive patterns, these simulations can provide insight into the genetic health of a population over time. Monte Carlo simulations help determine the minimum population size needed to maintain genetic diversity and prevent inbreeding depression. They also take into account possible random events, such as accidents or disease, that could affect the population. Such modeling is essential to creating a sustainable human colony that can thrive for centuries. Maintaining genetic diversity requires careful planning of reproductive strategies and potential genetic screening. The crew must be educated about the importance of genetic health and the steps necessary to maintain it. This includes monitoring genetic diversity and making informed decisions about partnership and reproduction. Research shows that a minimum initial population of at least 100 individuals is required to maintain genetic health over several generations. This figure comes from studies by scientists such as Frederick Moran and Camille Belufi, who have extensively studied the genetic dynamics of small isolated populations. In their research, Moran and Belufi use Monte Carlo simulations to explore different scenarios, including different population sizes and reproductive strategies. Their study shows that with a balanced sex ratio and optimal reproductive rate, an initial population of at least 100 individuals can maintain a healthy gene pool. This population size ensures that genetic drift and inbreeding will not jeopardize the health and viability of future generations. An initial population of 100 individuals should grow to 500 individuals over several generations. This growth is necessary to create a stable and resilient population that can cope with unforeseen challenges. The modeling takes into account various factors, such as random genetic mutations, environmental influences, and possible catastrophes to ensure the sustainability of the population. Designing a generational ship to accommodate a growing population involves planning for adequate living space, resources, and social structures. The ship should provide educational, health, and recreational facilities to support the physical and mental well-being of the crew. And this includes collaborative activity spaces and private living quarters to provide a balance between social interaction and personal privacy. Beyond the physical infrastructure, it's vital to maintain social cohesion and cultural continuity. The crew must develop a shared sense of purpose and identity to foster cooperation and sustainability. Cultural and educational programs play a key role in maintaining the knowledge and values necessary for mission success. Effective crew and population planning is essential to the success of a generational ship. Using advanced genetic simulations and research, we can ensure that the population remains healthy and viable. With careful planning and a commitment to maintaining social and genetic health, humanity can thrive on the path to the stars, ensuring the survival and prosperity of future generations. Above all, however, designing a generation ship capable of sustaining human life for centuries involves creating a self-sustaining environment that mimics the basic aspects of life on Earth. This includes creating artificial gravity, producing food, and recycling vital resources such as water and air. These systems must be reliable, efficient, and able to operate autonomously for long periods. One of the most important aspects of ship design is the creation of artificial gravity to maintain the health and wellness of the crew. Prolonged exposure to microgravity can lead to muscle atrophy, loss of bone density, and other health problems. To counteract these effects, generation ships can use rotating media to create a centrifugal force that mimics Earth's gravity. The most practical design involves a large rotating ring or cylindrical section where the crew lives and works. As the structure rotates at a certain speed, centrifugal force pushes the occupants outward, simulating the effect of gravity. For example, a ring with a radius of 100 yards must rotate at a rate of about 3 revolutions per minute to create an artificial gravity of 1 g, similar to Earth's. This design not only helps maintain physical health, but also provides a familiar environment that can alleviate the psychological challenges of living in space. Rotating habitats can include living quarters, recreational areas, and workspaces designed to optimize the use of available space and resources. Reliable and efficient food production systems are also required to sustain populations for generations to come. Hydroponic and aeroponic systems offer solutions for growing crops without soil, using nutrient-rich water or mist to nourish the plants. These methods are highly efficient, use less water and space than traditional farming, and are well suited to the controlled environment of our ship. Hydroponic systems involve growing plants in nutrient solutions with their roots suspended in water. Aeroponic systems, on the other hand, use a fine mist to deliver nutrients directly to the roots. Both systems can grow a wide range of crops, from leafy greens to root vegetables, providing balanced nutrition for the crew. These systems can be automated and monitored to maintain optimal growing conditions, ensuring a stable and reliable food supply. In addition, genetic modification and breeding will be able to increase the yield and nutritional value of crops. Efficient water and air recycling is critical to the sustainability of a generation ship. Water recycling systems must be capable of recovering and treating wastewater, ensuring a continuous supply of clean water for drinking, cooking, and irrigation. Advanced filtration and purification technologies, such as those used on the International Space Station, are already achieving high levels of efficiency. On the ISS, for example, the water reclamation system can recycle up to 98% of wastewater, including urine and sweat. This level of efficiency is necessary for long-duration missions when resupply from Earth is not feasible. Ships of future generations will need to improve this efficiency even further, aiming for near-complete recycling to minimize the need for large water reserves. Air recycling is equally important, requiring systems that can remove carbon dioxide and replenish oxygen. Natural systems, such as photosynthesis in plants, can be integrated with artificial CO2 scrubbers to maintain a balanced atmosphere. Plants, in turn, not only provide oxygen but also contribute to the psychological well-being of the crew by providing a connection to nature. Projects such as Biosphere 2 have demonstrated the potential for creating closed ecosystems in which plants, humans, and microorganisms coexist by recycling air, water, and nutrients. Although Biosphere 2 faced some challenges, it demonstrated the feasibility of such systems, providing valuable lessons for the design of life support systems on generational ships. Creating a self-sustaining generational ship requires integrating advanced technology with natural processes to ensure the health and well-being of its inhabitants. Artificial gravity, efficient food production, and reliable disposal systems are the very pillars of this design, enabling humanity to embark on a long-term journey to the stars. Ensuring the success of a multi-generational mission goes beyond the physical and technological aspects of the ship. It requires meeting the mental, social, and educational needs of the crew, ensuring their health, motivation, and cohesion throughout the long voyage. Isolation and confined spaces can significantly affect morale and mental health. Lack of new stimuli and prolonged separation from Earth can lead to feelings of loneliness, depression, and anxiety. Addressing these issues is critical to maintaining a stable and motivated crew. Virtual reality technologies offer promising solutions for mental health and cultural connection. By creating immersive simulations of terrestrial environments, virtual reality or VR can provide a sense of escape and familiarity. Crew members will be able to see forests, oceans, and even social gatherings, helping to alleviate feelings of isolation and to maintain a connection to their home planet. Artificial intelligence can also play an important role in supporting crew mental health. AI therapists, such as NASA's Simon 2.0, can offer individual counseling, monitor psychological well-being, and suggest strategies for coping with stress and interpersonal conflict. These AI systems can adapt and learn from each generation, providing continuity and consistency in mental health support. Ensuring the intergenerational transfer of knowledge and skills is critical to mission sustainability. A comprehensive education system must be put into place to ensure that each new generation receives the necessary skills to operate and maintain the ship, as well as the knowledge to continue research and exploration. This should include formal education, practical training, and the preservation of cultural and historical knowledge. Embarking on an interstellar voyage requires not only technological prowess, but also a deep commitment to the human spirit. By addressing the mental, social, and educational needs of the crew, we ensure the resilience and connection of each generation that carries the torch of exploration and survival. Advanced technologies such as virtual reality and artificial intelligence support, combined with strong cultural and social structures, will create the foundation for a thriving community across generations. When we reach beyond our solar system, a harmonious blend of innovation and humanity will lead us to new worlds, securing our future as an interstellar species. What if the relentless forward march of time, the ticking of seconds, the changing of seasons, the aging of our bodies, is nothing more than a grand illusion? What if the past, present, and future, the cornerstones of our existence, don't truly exist in the way we believe? For centuries, these questions have haunted philosophers, scientists, and everyday minds alike. Is time woven into the very fabric of reality, or is it a stubbornly persistent trick our brains play on us? The deeper we delve into the mysteries of the cosmos, the more a tantalizing possibility emerges. What if our entire reality is a simulation? If so, could time simply be a programmed construct, a line of code within a vast, artificial universe? This concept forces us to question everything, even our most fundamental assumptions about the passage of moments. We often take time for granted, but it shares a surprising similarity with another constant in our lives: color. The colors we perceive are not inherent properties of objects themselves. Instead, they're creations of our brains as they interpret wavelengths of light. Could a similar process be happening with time? Perhaps our sense of temporal flow is a construct, a way for our minds to impose order and meaning on an otherwise timeless universe. Consider the vibrant world of color that surrounds us. A juicy red apple, a field of yellow sunflowers, clear blue of a summer sky. At first glance, these colors might seem like fixed properties of the objects themselves. Yet the reality is far more complex. Colors don't exist independently in the world. They're born within our minds. Our eyes detect different wavelengths of light, and our brains translate those signals into the rich tapestry of hues that shape our visual experience. This process isn't merely about biology. People with different forms of color blindness perceive the world in distinct ways. Animals with different eye structures experience an even wider range of colors, some even seeing wavelengths invisible to us. What we call color is highly subjective, shaped by the unique capabilities of our sensory systems. Just as our perception of color is a creation of our minds, could the same be true of time? Perhaps the feeling of time ceaselessly flowing forward, the division of our lives into past, present, and future, is merely a way to make sense of change within the universe. Maybe, like color, time emerges from the interaction between our consciousness and a reality that may be fundamentally timeless. The idea that time may be an illusion isn't new. From ancient philosophers grappling with the nature of change to modern physicists unraveling the fabric of space-time, the question of time has persistently challenged our understanding. Today, we're going to delve into this enigma, exploring the scientific discoveries and philosophical riddles that hint at the possibility that time, as we experience it, may be nothing more than a grand cosmic deception. Time feels inescapable. It permeates our lives, from alarm clocks jolting us awake to the relentless countdown to birthdays and deadlines. We measure our existence in seconds, minutes, and years, accepting this flow of time as an absolute, unyielding force. For centuries, this intuitive understanding of time was reinforced by the ideas of Sir Isaac Newton. He envisioned the universe as a vast stage with time serving as a universal clock, ticking away at the same steady rate for everyone and everything. But then came Albert Einstein, and our understanding of time was forever shattered. Einstein's theory of relativity revealed that time isn't a rigid constant, but a flexible participant in the cosmic dance. It bends, stretches, and warps depending on how fast you're moving and the strength of gravity's embrace. Imagine two identical clocks, one placed on Earth, the other aboard a spaceship hurtling near the speed of light. Bizarrely, if you could compare them, the clock on the spaceship would be ticking slower than the one on Earth. This mind-bending concept is time dilation. The faster you travel through space, the slower you travel through time. This isn't some abstract theory. It has real consequences. Imagine twins separated at birth. One stays on Earth, the other becomes an astronaut who spends years traveling at immense speeds. Upon their reunion, the spacefaring twin would have aged less than their Earth-bound sibling. Time would have literally passed slower for them due to the effects of time dilation. Time dilation may seem like science fiction, but it's a fact of our universe that engineers have to account for. GPS satellites, orbiting high above Earth and traveling at significant speeds, experience time slightly slower than we do on the ground. Their onboard clocks have to be adjusted to stay in sync, ensuring the maps on your phone remain accurate. Einstein's revolutionary theories upended our understanding of time. Suddenly, time wasn't a steady constant, but a dynamic player in the cosmic drama. This scientific upheaval sparked a resurgence in philosophical debates about the very nature of time. If time dilation and warped space-time are real, how do we reconcile these concepts with our everyday experience of time's constant flow? Let's explore some of the profound questions that emerge at the intersection of physics and philosophy. One central debate centers on the existence of the past and future. Presentists argue that only the present moment has any real existence. The past is a collection of memories, the future a realm of possibilities. Eternalists take the opposite stance, viewing all of the time, past, present, and future, as equally real and unchanging, like a vast unfurling tapestry. The growing block universe model attempts to bridge these two views. It posits a fixed past, an open future constantly branching into possibilities, and a continuously expanding present moment as our experience unfolds. These seemingly abstract philosophical debates have profound implications. If only the present exists, how can we learn from the past or plan for the future? If the future is already set, does that negate free will? The way we conceptualize time shapes how we understand our place in the universe and the choices we make within it. Perhaps the most unsettling implication of the block universe is the challenge it poses to free will. If the future already exists, laid out like a vast network of paths, are our choices truly our own? Or are we merely tracing a predetermined route? Our sense of agency nothing more than an illusion? This paradox forces us to grapple with the question of what it means to have control over our destiny within a universe where all moments may already be written. Can the block universe coexist with genuine free will? Some philosophers argue that even if our actions are fixed within a timeless expanse, we still experience the act of choosing and the consequences of those choices. Others suggest that true freedom might lie in accepting the predetermined nature of existence and finding meaning within that framework. Why does time seem to relentlessly march forward, never backward? Physicists and philosophers grapple with different arrows of time, each offering clues to the irreversible nature of events. The thermodynamic arrow is one of the most well-known. It stems from the second law of thermodynamics, which states that entropy, a measure of disorder, always increases in a closed system. This explains why eggs break but never unbreak, and why ice melts but doesn't spontaneously refreeze. Irreversible processes give us our sense of time moving in one direction. But thermodynamics isn't the whole story. Our minds create a powerful psychological arrow of time. We vividly remember the past, yet the future remains a mystery. Even the universe itself provides a cosmological arrow, as it continues to expand outward since the Big Bang. These diverse arrows raise a perplexing question. Is the flow of time a fundamental property of the universe, or a byproduct of how we experience the relentless unfolding of change? The bizarre realm of quantum mechanics throws a wrench into our traditional understanding of time and space. Consider the phenomena of entanglement, where two particles become linked in a profound way. Imagine a pair of gloves, one for your left hand, the other for your right. If those gloves are separated and placed in boxes on opposite sides of the planet, they remain intrinsically connected. If you open one box and find a right-handed glove, you instantaneously know, faster than any signal could travel, that the other box contains the left-handed glove. In the quantum realm, particles can become similarly entangled, their properties inextricably linked. Measuring one instantly affects the other, even across vast distances, seemingly faster than the speed of light allows. This paradox hints at a universe where connections might exist outside our usual understanding of linear time. Theories like loop quantum gravity go even further, suggesting space-time itself isn't a smooth continuum, but made up of tiny, indivisible chunks like the threads of a cosmic tapestry. If true, time might not be a fundamental force, but rather an emergent property of this deeper structure, a byproduct of the way these fundamental building blocks interact. These mind-bending theories force us to question the very nature of reality. Could it be that our experience of time's relentless flow is an illusion, born from our limited perspective within a universe that may operate on principles beyond our current comprehension? Perhaps the past, present, and future we perceive are merely convenient ways for our minds to organize the chaotic dance of existence. The true nature of time remains one of the universe's greatest enigmas. Is it a fundamental force woven into the fabric of existence, guiding the destinies of planets and particles alike? Or is it a grand illusion? A convenient fiction created by our own limited perspective? Scientific discoveries and philosophical paradoxes hint at the possibility that our experience of time's flow may be profoundly different from the true reality of the cosmos. If time doesn't exist as we perceive it, what does that mean for free will and our place within the grand story of the universe? Are the past, present, and future simply emergent constructs in a reality governed by laws beyond our current grasp? We may never possess the definitive answers to these questions, but the very act of pondering them reveals the profound beauty and endless mystery of existence. While the relentless march of the clock and the turning of the calendar may shape our daily lives, perhaps true freedom lies in embracing the timeless wonder of a universe that continually defies our understanding. In a universe dominated by ancient massive structures, there are places where something unexpected happens that defies the cosmic norm. New galaxies emerge. These rare formations are changing our idea of how the cosmos should behave. While the Milky Way and Andromeda seem to have entered their mature phase, somewhere out there in the far corners of space, young galaxies are still being born, glowing with the energy of new star formation. But why do these exceptions exist? What forces allow them to thrive when the rest of the universe has slowed down? By exploring these distant regions, we learn about the forces that lead to the formation of such grand structures, the role of dark matter in all of this, and the mysterious processes that allow some galaxies to defy the passage of time. The discovery and classification of galaxies was a milestone in our understanding of the universe. In the early 20th century, observations by Edwin Hubble showed that the nebulae observed in telescopes were not just gas clouds inside our galaxy, but entire galaxies, each containing billions of stars. This discovery expanded our understanding of the cosmos beyond the Milky Way, revealing a universe teeming with distant galaxies. Soon, galaxies were categorized by their shape: spiral, elliptical, and irregular. These classifications helped astronomers create a more organized view of the cosmos, which led to further study of the origin and evolution of these huge structures. However, as our observations deepened, a surprising pattern emerged. The vast majority of galaxies observed were ancient, dating back almost to the very beginning of the universe. This discovery was unexpected. When the first detailed studies of galaxies were conducted, scientists expected to find a range of galaxy ages, including recently formed galaxies. However, instead of a universe full of young galaxies still in the formation stage, they found that most galaxies had already reached maturity. These findings challenged existing theories of cosmic evolution at the time, raising questions about how and when galaxies formed. At first, the scientific community was stunned. The rarity of young galaxies seemed to contradict the ongoing process of star formation that's still observed in the universe today. This paradox, the presence of ongoing star formation in predominantly ancient galaxies, posed a serious question to our understanding of galaxy formation and evolution. As astronomers delved deeper into this mystery, they began to realize that the formation of galaxies may not be as simple as previously thought. The processes that govern the early universe, such as the distribution of dark matter and the influence of cosmic structures, seem to have played a more important role in shaping its landscape than first thought. These factors likely contributed to the rapid formation of galaxies shortly after the Big Bang, leading to a shortage of newly formed ones in the modern era. Determining the age of galaxies is a complex task that relies on a variety of methods, most of which focus on the age of the stars within them. For example, astronomers have used several methods to estimate the age of the stellar population of the Milky Way and Andromeda. One of the main methods involves studying the distribution of stars in the Hertzsprung-Russell diagram, or HR diagram, which shows the dependence of the luminosity of stars on their temperature. In particular, astronomers focus on the turning point of the main sequence, the stage at which stars begin to leave the main sequence and turn into red giants. This point is very sensitive to age. The position of the pivot point on the HR diagram can give an accurate estimate of the age of the stellar population. Another important method is the study of globular clusters, dense groups of ancient stars orbiting around the outskirts of galaxies. The age of these clusters is also determined by the rotation points of the main sequence of their stars. And since globular clusters are among the oldest objects in the galaxy, they provide crucial clues about their formation history. For example, the oldest globular clusters in the Milky Way are about 13 billion years old, indicating that the Milky Way itself formed shortly after the Big Bang. In addition to studying star clusters, astronomers also use spectral analysis. By analyzing light spectra, particularly absorption lines, they can determine the relative proportions of different types of stars. Older galaxies are dominated by red, cooler stars, while younger galaxies have more blue, hotter stars. The discovery that many galaxies, including the Milky Way, formed nearly 13.8 billion years ago, shortly after the Big Bang, was a significant breakthrough in cosmology. The rapid collapse of clouds of primordial gas under the influence of dark matter probably played a crucial role in these early formations. This process laid the foundation for the cosmic structures we see today. So the formation of galaxies in the early universe is a story deeply intertwined with the mysterious and influential presence of dark matter. In the chaotic period after the Big Bang, the universe was a hot, dense soup of particles in which matter and radiation were tightly bound together. As the universe expanded and cooled, gravity began to pull matter together into the first structures, tiny clumps of matter, known as proto-galaxies. According to scientists, dark matter played a key role in this process. Unlike ordinary matter, which interacts through the electromagnetic forces and radiation, dark matter interacts mainly through gravity. Because of this, dark matter began to stick together earlier than ordinary matter, forming the basis on which the first galaxies eventually formed. These dense regions of dark matter, often called dark matter halos, provided the gravitational wells needed to pull in gas and dust, leading to the formation of the first stars and eventually the first galaxies. These early galaxies were relatively small and simple compared to the huge and complex galaxies we see today. They were often irregularly shaped and lacking a distinct structure, such as that of the Milky Way. But over time, driven by the gravitational pull of dark matter, these proto-galaxies began to merge and interact. As proto-galaxies merged, they grew in size and complexity, forming more massive structures that eventually evolved into the spirals, ellipticals, and irregular shapes that populate the modern universe. This period of intense formation and merger is often referred to as cosmic noon, a time of active star formation and growth through mergers at a much higher rate than we observe in the modern universe. So why are newly formed galaxies such a rarity in the modern universe? One of the key factors contributing to this phenomenon was the very process of galaxy mergers. In the early universe, when galaxies were smaller and more numerous, there were frequent interactions and collisions between them. However, as the universe expanded and matured, such collisions became less frequent, resulting in fewer new galaxies. Another factor is the changing influence of dark matter halos. In the early universe, halos were smaller and more concentrated, favoring the collapse of gas and the formation of new stars and galaxies. As the universe expanded, it became larger and more diffuse, making it harder for the gas to cool and condense into new formations. The large-scale structure of the universe, often referred to as the cosmic web, also plays a notable role in this process. Galaxies are not randomly distributed, but are arranged along huge threads of dark matter that stretch across the cosmos, connecting galaxy clusters. Along these threads, gas flows into them, fueling the star formation process. However, in the present epoch, most of the gas has already been consumed or trapped in larger and more stable structures, which also leads to a decrease in the rate of new formation. However, despite all that we've just said, there are rare cases that violate this trend. One such example is the dwarf irregular galaxy known as Zwicky 18. Located about 45 million light-years away, this galaxy is notable for having a relatively recent burst of star formation. Unlike most, Zwicky 18 began its first major burst of star formation only about 500 million years ago, well after the period when most galaxies in the universe were fully formed. The slow evolution of Zwicky 18 represents an intriguing case in the study of galaxy formation. Its star-forming regions are characterized by intense ultraviolet emission and stellar winds from young massive stars. The presence of these young stars, combined with the overall low metallicity, suggests that Zwicky 18 did not undergo the same evolutionary processes as most other galaxies. This late bloom may provide clues to the conditions favoring delayed star formation and raise the question of the role of environmental factors, such as nearby galaxy interactions in triggering or suppressing star formation. Another notable case is a galaxy with a rather unwieldy name of HSC J1631 plus 4426. discovered through observations with a Subaru telescope, located 430 million light-years away. This specimen is not only young, but also holds the record for the lowest observed oxygen content. The low oxygen content indicates that the galaxy is in the very early stages of its formation and has only recently begun to convert primordial hydrogen and helium into heavier elements through stellar nucleosynthesis. The galaxy's small size, about 0.8 million solar masses, comparable to a star cluster in our Milky Way, further emphasizes its youth. The fact that such a young and small specimen exists so late in the history of the universe is surprising, given that in the early universe, the conditions for galaxy formation were much more favorable. And given that the expansion of the universe continues to accelerate, making conditions for the formation of new galaxies more and more impossible, such findings become quite extraordinary. At the same time, star formation is a continuous process that continues even in ancient galaxies. And star clusters such as the Pleiades provide clear evidence of this ongoing activity. The Pleiades, often referred to as the Seven Sisters, is a young open star cluster located just 448 light-years from Earth. Despite the age of the Milky Way galaxy being over 13 billion years old, the Pleiades cluster is a relative newcomer, having formed only about 100 million years ago. This indicates that even in such a mature galaxy as ours, there are still regions of active star formation. The formation of star clusters like the Pleiades usually occurs in regions of galaxies where there's a high concentration of gas and dust. These molecular clouds collapse under their gravity, giving birth to new stars. In the case of the Pleiades, the stars of the cluster are still relatively young and hot, and they emit bright blue light, making the cluster visible to the naked eye. Such star clusters are not unique to our galaxy. In neighboring galaxies, such as the Large Magellanic Cloud, abbreviated LMC, star formation is also ongoing. The LMC, a companion galaxy to the Milky Way, contains the oldest known stars as well as regions where new ones are still forming. One such ancient star, LMC 119, that was only discovered this year, is believed by scientists to be about 13 billion years old. This discovery highlights the remarkable longevity of some stars and suggests the conditions for star formation are still not fully understood by us. These star-forming regions are not just remnants of the past, but a critical factor in the future evolution of galaxies. As new stars form, they contribute to ongoing dynamical processes in their host galaxies, affecting everything from the formation of planetary systems to the distribution of elements necessary for life. While star formation continues in some regions of galaxies, like the Milky Way, a significant factor affecting the overall evolution of these galaxies is the presence of the previously mentioned dark matter halos. These halos extend far beyond the visible edges of galaxies and play a crucial role in their formation and structure. As we know, dark matter has a significant gravitational influence on galaxies. This influence is most evident in the way galaxies rotate. Observations have shown that the outer regions of spiral galaxies, including the Milky Way, rotate much faster than would be expected with only visible matter. This discrepancy suggests the presence of a massive invisible component forming a spherical halo around the galaxy. The dark matter halo not only stabilizes galaxies, but also affects their ability to form new stars, and, consequently, new galaxies. In the early universe, dark matter halos provided the gravitational wells necessary for the collapse of gas and the formation of the first galaxies. Over time, however, these halos grew in size and became more diffuse, preventing the formation of new galaxies. The expanding halos, with their enormous gravitational influence, can prevent the gas from cooling and condensing into new stars, effectively suppressing the birth of new galaxies in the current epoch. These dynamics create a delicate balance in the cosmos, where dark matter both promotes and inhibits the growth of cosmic structures. According to scientists, the presence of such halos is one of the key reasons why we see fewer new galaxies forming today compared to the early universe, marking a significant shift in cosmic evolution. Understanding the formation and evolution of galaxies remains one of the most serious challenges of cosmology. Despite significant progress, debates about the fundamental processes that shape the universe are still ongoing. One of the key debates concerns the formation of structures in the cosmos, whether it occurs according to the top-down or bottom-up approach. According to the top-down model, large cosmic structures form first, and then they break up into smaller galaxies and clusters. According to this model, the largest galaxies and galaxy clusters appeared at the very beginning of the universe's history, and smaller structures were formed as these large structures decayed. In contrast, the bottom-up model suggests that small structures formed first, and tiny proto-galaxies and star clusters eventually merged to form larger galaxies and clusters. This theory is consistent with the observed hierarchical nature of the universe, where small objects merge into more complex and massive systems over billions of years. Although these models provide a foundation for understanding galaxy formation, recent observations have revealed complexities that challenge both theories. For example, the discovery of ancient massive galaxies in the early universe suggests a more subtle interaction between these processes, perhaps indicating that the true nature of cosmic evolution is a combination of both scenarios. Nevertheless, the search for and understanding of new galaxies continues to drive astronomical research. JWST has already opened new windows into the distant universe, allowing astronomers to peer into an era when galaxies were just forming. One of the most intriguing questions is whether new galaxies are still forming today. While the early universe was fertile ground for galaxies to form, today's cosmic landscape presents a different picture. As the universe expands and dark energy accelerates this expansion, conditions suitable for galaxy formation become increasingly rare. Future astronomical missions are poised to push the boundaries of our knowledge even further. Instruments such as the Vera C. Rubin Observatory and the European Space Agency's Euclid mission will shortly carry out deep space surveys that are likely to reveal new galaxies that have eluded previous observations. These missions are aimed not only at discovering new galaxies, but also at unlocking the mysteries of dark matter, dark energy, and the overarching structure of the universe. History of the universe is far from complete. As we continue to explore the cosmos, discoveries change our understanding and raise new questions. Each glimpse into the distant past brings us closer to unraveling the mysteries of the universe's formation and fate. Stay tuned for more discoveries to come.